Imagine a vast, swirling cloud of gas and dust surrounding a young, blazing star in the depths of space. This cosmic nursery is known as a protoplanetary disk, a birthplace for planets, moons, and the fundamental building blocks of solar systems. Each of these disks represents a snapshot of creation, a raw beginning, where gravity, chemistry, and time all played pivotal roles in the birth of planets. Observing them gives scientists a direct view into the mysteries of how planetary systems, like our own, come into existence, giving us clues about our origins and the countless alien worlds scattered across the universe. Understanding the journey from particles of dust to fully formed planets offers one of the most captivating tales of cosmic evolution, filled with intricate processes and remarkable transformations. But before we continue, if you like this type of videos, please subscribe to the channel and comment. These disks, often spanning hundreds of millions of miles, provide essential insight into how matter coalesces under the laws of physics to form everything from tiny dust grains to massive gas giants. Through powerful telescopes and advanced imaging, astronomers can observe these distant regions and witness the early stages of planet formation. Protoplanetary disks shine a light on the very forces that shaped our solar system and countless others throughout the cosmos. Observing and analyzing these distant objects tells us about the conditions necessary for planetary formation and reveals the processes that give birth to worlds vastly different from our own. At the core of the mystery surrounding protoplanetary disks is an intricate set of processes that play out over millions of years. Initially, the disk is composed of gas and tiny dust grains, remnants from the molecular cloud from which the star itself was born. Under the influence of the star's gravitational pull, this material begins to settle into a flattened, rotating disk. Within this spinning, turbulent cloud, countless interactions occur, triggering a chain reaction of growth and change that eventually leads to the formation of planetary bodies. Over time, tiny particles collide and stick together, forming clumps that grow larger and larger. Eventually, these clumps reach sizes that can be measured in miles, becoming planetesimals, the essential building blocks of planets. The journey from dust particle to planetesimal is a delicate and complex process influenced by various forces. When particles within the disk collide, they may stick together due to static forces if the particles are small enough, or coalesce due to gravity if they are larger. In the dense regions of the disk, these particles begin to clump together and grow in size, often fusing upon impact, especially if they encounter a similar composition. As more material collects, these early building blocks develop a gravitational pull of their own, further accelerating the accumulation of nearby dust and particles. Yet, this is only the beginning. The newly formed planetesimals, having gathered substantial mass, now begin to interact gravitationally with the surrounding disk. In some cases, these early bodies may experience collisions with each other, breaking apart or fusing to form even larger entities. This process of accretion, where matter is gathered by gravitational attraction, continues until some of these objects reach a scale where they can be considered protoplanets. The journey from protoplanetary disk to fully formed planets can vary dramatically depending on the disk's properties, the star's radiation, and the complex interactions between developing celestial bodies. One of the critical aspects of planet formation within a protoplanetary disk is the differentiation between rocky planets, like Earth and Mars, and gas giants, such as Jupiter and Saturn. Near the young star, temperatures are extremely high, preventing volatile substances like water and methane from condensing into solid form. As a result, planets forming close to the star tend to be rocky, composed primarily of metals and silicates. These inner planets, often referred to as terrestrial planets, are small in size but dense, with solid surfaces that can potentially harbor atmospheres if conditions are right. Farther from the star, in the cooler regions of the disk, gas and ice can condense into solid forms, allowing for the formation of gas giants. Here, icy planetesimals accumulate, eventually forming massive cores that can capture vast amounts of gas from the surrounding disk. This gas accumulation process is what differentiates gas giants from terrestrial planets. In some cases, these giant planets can even migrate inward due to gravitational interactions with the disk, altering the arrangement of planets within a developing solar system. Observing protoplanetary disks is like peering back in time to the origins of our solar system. Through advanced telescopes such as the Atacama Large Millimeter/Submillimeter Array, ALMA, and the Hubble Space Telescope, scientists can study these distant, young systems in remarkable detail. ALMA, in particular, has transformed our understanding by allowing astronomers to capture high-resolution images of protoplanetary disks, revealing intricate rings and gaps that may signal the presence of forming planets. Each gap is thought to be carved out by a planet that has reached sufficient size to clear out its orbit, creating a pathway in the disk. These gaps are one of the strongest indicators of planets in formation, acting as signposts of the activity taking place within the disk. One of the mysteries that scientists continue to explore is how the composition of a protoplanetary disk influences the types of planets that form within it. By analyzing the light spectra emitted or absorbed by these disks, researchers can determine the composition of the gas and dust within them. This chemical fingerprint helps scientists understand how different elements contribute to planetary formation and the likelihood of certain types of planets emerging. For instance, disks rich in carbon may give rise to planets with different atmospheric compositions compared to those found in oxygen-dominant environments. Studying these factors provides a window into how diverse planetary systems could be and raises the question of what unique types of worlds might exist beyond our solar system. The study of protoplanetary disks also leads scientists to question the origin of water and organic compounds, key ingredients for life as we know it. In the early stages of planet formation, water ice is believed to be abundant in the colder outer regions of the disk. This water can become incorporated into developing planets or icy bodies, possibly delivering water to terrestrial planets closer to the star through migration or impacts. This process might explain how Earth acquired its oceans, as icy planetesimals and comets from the outer regions of the early solar system collided with the young Earth, bringing water and organic molecules essential for life. The presence of similar conditions in other disks suggests that water-bearing planets may not be rare, expanding the potential for habitable worlds elsewhere. Additionally, by examining young stars with varying masses and ages, scientists are beginning to understand the influence of a star's properties on its disk and the resulting planetary system. Stars of different masses produce different levels of radiation, which can affect the temperature and structure of the disk, influencing the size and type of planets that may form. For instance, massive stars with intense radiation may disperse the disk material more quickly, limiting the time available for planets to form. Conversely, lower mass stars with gentler radiation allow for longer periods of disk stability, which can result in a variety of planetary configurations. These variations highlight the diversity of planetary systems and hint at the numerous possibilities that exist across the cosmos. As protoplanetary disks evolve, they gradually dissipate, with much of the gas and dust either absorbed into forming planets, ejected into space, or blown away by the young star's radiation. Eventually, the once dense, swirling disk fades, leaving behind a newly formed planetary system. This process can take tens of millions of years, a relatively short period in cosmic terms, yet it represents a transformative stage that sets the foundation for billions of years of evolution. Observing disks at different stages of their evolution allows astronomers to piece together this timeline and make predictions about the life cycles of planetary systems. The information gleaned from studying protoplanetary disks holds the key to some of the most profound questions we can ask about the universe. How do planetary systems form? Why do they take on such diverse configurations? And how common are systems similar to our own? As astronomers continue to push the boundaries of observational technology, they uncover more about these ancient cosmic factories and the forces that shape them. Each new discovery helps refine our models of planet formation, bringing us closer to understanding the origins of our own solar system and, perhaps, the likelihood of life on distant worlds. In these spinning disks of gas and dust, scientists see not just the birthplaces of planets, but the seeds of potential life, the building blocks that could, under the right conditions, evolve into environments where complex organisms might arise. This possibility adds an extra layer of fascination to the study of protoplanetary disks, connecting the remote, silent reaches of space with the essential questions of existence. Every protoplanetary disk observed could be the start of a journey leading to planets rich with oceans, atmospheres, and perhaps even life. As scientists uncover more about the nature of these disks and the planets they give rise to, they also illuminate the interconnectedness of the universe, revealing that the forces shaping a distant solar system are not so different from those that shaped our own. The study of protoplanetary disks is more than an exploration of physics and chemistry. It's a search for the origins of worlds, and in that search, we uncover echoes of our own beginnings. Through the examination of protoplanetary disks, scientists are essentially mapping out the cosmic recipe for planet formation. The components in each disk, the gas, dust, ice, and various elements, play crucial roles in the eventual architecture of the planetary system. For example, the prevalence of silicates in the inner regions of disks can lead to the formation of rocky terrestrial planets, while the abundance of ice and gas in the cooler outer regions fosters the birth of gas giants. Over millions of years, the subtle dance of materials within these disks results in the formation of planets that vary dramatically in size, composition, and atmosphere. This leads to one of the most fascinating questions in astronomy. How do different initial conditions within a protoplanetary disk shape the unique attributes of a planetary system? One of the profound insights that has emerged from the study of these disks is the significance of a star's metallicity, or the amount of elements heavier than hydrogen and helium present in the star and surrounding disk. Stars with higher metallicity tend to produce protoplanetary disks richer in heavier elements, increasing the chances of planet formation. The more metal-rich a disk is, the more material there is to form planetesimals and, subsequently, full-size planets. Studies have shown that high metallicity stars are often associated with the presence of massive gas giants, suggesting that certain planetary types may be more likely around stars with specific compositions. This correlation between stellar composition and planetary system configuration has helped astronomers identify promising candidates for planet-hunting missions. The arrangement of planets within a developing solar system is influenced by another fascinating aspect of protoplanetary disks: migration. As young planets interact gravitationally with the disk, they often experience movement within it, either drifting closer to the central star or moving farther away. This planetary migration process has been observed in many extrasolar systems, where gas giants are sometimes found orbiting very close to their stars, a phenomenon that initially puzzled scientists. These hot Jupiters, for instance, are thought to have formed much farther from their stars, migrating inward due to interactions within the disk. This inward migration is an example of how dynamic and volatile the early stages of planetary development can be, with young planets constantly jostling for position within the disk. Observing these migrations and configurations reveals that the solar system we inhabit, with its clear arrangement of rocky planets near the Sun and gas giants farther out, is not necessarily the norm. Many planetary systems discovered to date are configured quite differently, with gas giants orbiting close to their host stars, while smaller, rocky planets are often found farther out or scattered in less predictable patterns. This diversity in planetary configurations illustrates that the processes governing the birth and arrangement of planets can yield a vast range of outcomes, with each protoplanetary disk producing a distinct planetary family based on its specific conditions. Furthermore, the study of protoplanetary disks offers insight into one of the most fundamental questions in astrobiology: the potential for life elsewhere in the universe. Scientists hypothesize that specific regions within these disks, known as ice lines or snow lines, play a crucial role in the potential development of life. An ice line is the distance from the star where temperatures are low enough for volatile compounds such as water, carbon dioxide, methane, and ammonia to freeze into solid ice. These compounds are critical for the formation of organic molecules, the essential ingredients for life. Planets forming near these ice lines may accumulate significant amounts of water and organic molecules, increasing the likelihood that they could eventually host life if conditions remain favorable. The position and existence of ice lines within a disk can have far-reaching implications for the types of planets that form and the availability of resources like water. For instance, in our own solar system, the frost line, the point beyond which temperatures are cold enough for water to freeze, was located between the orbits of Mars and Jupiter during the formation of our planetary neighborhood. This frost line contributed to the formation of gas giants in the outer solar system while leaving the inner region dominated by rocky planets. Understanding the distribution of ice lines in protoplanetary disks elsewhere offers hints about where we might find water-rich, potentially habitable exoplanets beyond our solar system. The advancements in telescope technology, particularly the use of infrared and radio wavelengths, have revolutionized our ability to observe these ice lines and the overall structure of protoplanetary disks. Instruments like the James Webb Space Telescope, JWST, and ALMA provide astronomers with unprecedented views of these disks, allowing them to identify specific regions where planet formation is actively taking place. These observations reveal not only the presence of planets but also clues about their composition, size, and distance from the central star. By studying the light that passes through or reflects off the disk, scientists can detect the molecular makeup of the gas and dust, identifying compounds like carbon monoxide, hydrogen cyanide, and water vapor. Each of these compounds carries implications for the types of planets that may form and whether they have the potential for supporting life. Another key discovery in recent years has been the detection of planet traps within protoplanetary disks. These traps are regions within the disk where material tends to accumulate, forming high-density areas that attract dust and gas, leading to accelerated planet formation. Planet traps are thought to play a crucial role in stabilizing forming planets, preventing them from migrating too close to the star where they would likely be vaporized. By analyzing these planet traps, scientists can gain insight into the likely positions and compositions of forming planets, helping them predict the overall structure of the eventual planetary system. Intriguingly, the study of protoplanetary disks also raises questions about the formation of moons and other secondary bodies within a planetary system. Many of the mechanisms that govern planetary formation also apply on a smaller scale, where material around a newly formed planet can coalesce into natural satellites. The formation of moons in a young planetary system offers further complexity, as moons themselves can influence the stability and development of their parent planets. Observations of gas giants like Jupiter and Saturn, which host numerous moons, suggest that large planets are likely to form complex satellite systems, adding another layer of diversity to planetary systems. The birth of a solar system is not merely the formation of planets, but the creation of a diverse collection of celestial bodies, each influencing one another through gravitational interactions. In our own solar system, for instance, Jupiter's immense gravity played a significant role in shaping the asteroid belt and may have even influenced the early formation of Earth and Mars. This intricate web of interactions is a hallmark of planetary systems and is a product of the initial conditions within the protoplanetary disk. Understanding these relationships allows scientists to create more accurate models of planetary evolution, shedding light on how systems develop stability over time and how certain configurations may lead to conditions suitable for life. Protoplanetary disks also provide a framework for understanding the early history of our own solar system. By studying disks around young stars, scientists can compare these developing systems to computer models of our solar system's formation, examining how various factors may have contributed to its unique structure. For instance, it's believed that the early solar system underwent a period known as the Late Heavy Bombardment, a time of intense collisions and impacts driven by the gravitational influence of the gas giants. Observing similar periods of instability in other young systems supports the idea that such violent phases may be a common feature of planetary formation, potentially playing a role in shaping planets' surfaces and compositions. As we peer into these disks, our understanding of the early solar system deepens, providing context for how Earth and its neighboring planets came to be. By connecting the processes within protoplanetary disks to the structure of established solar systems, scientists can piece together the story of our own origins, examining the ancient pathways that led from a cloud of interstellar gas and dust to a system of planets, asteroids, and comets orbiting a single star. The study of protoplanetary disks not only reveals clues about planetary origins but also highlights the delicate balance of forces that govern the stability and development of young planets. The disks themselves are dynamic, with material constantly moving, clumping, dispersing, and reshaping under the influence of gravity, radiation, and magnetic forces. This delicate environment is fraught with challenges for emerging planets, which must contend with collisions, intense radiation from the young star, and the risk of being drawn into it by gravitational forces. In these turbulent environments, planet formation is a race against time. A protoplanetary disk exists for only a few million years, a short period in cosmic terms. During this time, planets must accumulate enough mass to survive after the disk disperses, which happens as the young star's radiation and stellar winds blow away the remaining gas and dust. If a planet doesn't gather enough material before the disk dissipates, it may end up as a small, rocky body with limited atmosphere, much like Mercury. In contrast, planets that quickly accrue substantial amounts of gas and dust can become massive gas giants, accumulating thick atmospheres and extended systems of rings and moons. Once the protoplanetary disk begins to dissipate, the process of planet formation doesn't simply end, rather, it evolves. The young planets enter a phase of planetary migration, where their orbits may shift due to residual interactions within the disk and gravitational influences from neighboring planets. This migration can radically alter the layout of the planetary system. Planets that formed far from the star might move inward, creating configurations that seem almost impossible when compared to our solar system's orderly arrangement. In some systems, massive gas giants migrate so close to their star that their atmospheres start to evaporate due to the intense heat, creating exotic worlds known as hot Jupiters. As scientists continue to observe and analyze protoplanetary disks, they've discovered that the migration of planets isn't just a random occurrence. It follows patterns based on disk density, temperature gradients, and the mass of forming planets. In some cases, planets may even settle into stable, resonant orbits, where their gravitational interactions with each other create a balanced configuration. This phenomenon, observed in systems like the TRAPPIST-1 system, showcases how intricate and harmonious planetary systems can become as they evolve, settling into configurations that might last for billions of years. Observing these migratory patterns is crucial for understanding how planets reach their final positions and how planetary systems achieve stability over time. In our own solar system, for instance, Jupiter and Saturn's gravitational influence may have helped stabilize the orbits of the inner planets, preventing them from colliding with each other or being flung out of the system. The gravitational interplay among planets within a disk also influences the formation of minor bodies, such as comets and asteroids, which may later play a role in delivering water and organic materials to young terrestrial planets. The study of these disks provides insight into the diversity of planetary types and their compositions. The inner regions of a disk, where temperatures are higher, favor the formation of rocky, metallic bodies as only materials with high melting points can condense there. Conversely, in the cooler outer regions, lighter elements and compounds, such as hydrogen, helium, and ices, remain stable, enabling the formation of gas giants and ice giants. This temperature gradient helps explain the range of planet types we observe, from rocky Earth-like planets to massive gas giants like Jupiter and Saturn, and even icy bodies like Neptune and Uranus. Another intriguing aspect of protoplanetary disks is the presence of complex organic molecules, including those that could be precursors to life. Observations from telescopes like ALMA have revealed that some disks contain molecules such as amino acids, which are essential building blocks of life. The fact that these molecules can form in the cold, distant regions of a disk around a young star suggests that the ingredients for life may be far more common than once thought. This discovery opens up possibilities for the emergence of life on planets that form within these disks, especially if they reside in a habitable zone, where temperatures allow liquid water to exist. In some cases, the organic materials found within protoplanetary disks can become embedded within icy comets or asteroids. These bodies, once they form, may be scattered throughout the planetary system during its chaotic early stages. If they eventually collide with a young, developing planet, they could deliver these organic compounds, seeding it with the raw materials necessary for life to evolve. This theory, known as panspermia, posits that life's ingredients may not be limited to one particular planet but could be spread across a solar system, or even between star systems, by interstellar debris. The wealth of data gathered from observing protoplanetary disks also allows scientists to simulate planet formation through sophisticated computer models. These models incorporate variables such as disk density, temperature, and chemical composition, aiming to replicate the complex processes within a disk. By comparing the outcomes of these simulations with observed exoplanetary systems, scientists can refine their understanding of planet formation, honing in on the specific factors that lead to the emergence of various types of planets and system architectures. Simulations have revealed that small differences in the initial conditions of a disk can result in vastly different outcomes, demonstrating the sensitivity of planetary formation to its environment. For instance, a disk with a slightly higher concentration of dust might form a super-Earth, while a disk with more gas might yield a Neptune-like ice giant. The findings from these models suggest that every planetary system is a unique product of its environment, shaped by the specific makeup of its protoplanetary disk and the particular dynamics that play out during its early stages. Perhaps one of the most profound implications of studying protoplanetary disks is the insight it offers into the frequency of Earth-like planets. By observing a wide variety of disks and examining the prevalence of rocky planets forming in the habitable zones around other stars, scientists can estimate the likelihood of Earth-like worlds existing throughout the galaxy. If conditions conducive to the formation of terrestrial planets are common in protoplanetary disks, it stands to reason that planets with the potential to support life may be abundant as well. The quest to understand protoplanetary disks and the birth of planets is not only a journey into the origins of solar systems, but also a window into our own cosmic heritage. The processes observed within these disks, collisions, migrations, the accumulation of materials, and the formation of stable planetary orbits, are the same processes that ultimately led to the formation of Earth, providing the conditions necessary for life to emerge and thrive. As new telescopes and observational technologies come online, our ability to study these disks in greater detail will continue to advance. Future missions, such as those involving space-based interferometry, will provide even more precise measurements of the structure and composition of these disks, revealing ever more intricate details of planet formation. By examining these snapshots of planetary nurseries, scientists can refine their models, deepen their understanding, and perhaps even answer some of the most profound questions about our place in the cosmos. In the vast, cold depths of space, where protoplanetary disks drift silently around young stars, the birth of planets unfolds with a quiet intensity. Dust and gas coalesce under gravity's pull, collisions and accretions build world upon world, and the seeds of entire solar systems take shape. Observing this process offers us a glimpse into the beginnings of not only planets and moons but the conditions that one day, somewhere, may lead to life as we know it. Protoplanetary disks serve as both the cradle and the canvas for the countless worlds scattered across the universe, each one a testament to the enduring, intricate, and awe-inspiring process of cosmic creation. As we continue to uncover the secrets of protoplanetary disks, we learn more about how these cosmic nurseries hold the building blocks for entire solar systems. One of the most fascinating aspects of these disks is their incredible variety. No two protoplanetary disks are exactly alike, and this uniqueness significantly affects the types of planets they produce. For instance, some disks are much denser or more extensive than others, leading to the formation of larger planets or more expansive planetary systems. The diversity in disk characteristics points to the countless ways planetary systems can evolve, showcasing nature's creativity and adaptability on a cosmic scale. One key factor influencing the development of planets within these disks is the initial mass of the disk. A more massive disk has more material to work with, which increases the likelihood of forming giant planets like Jupiter and Saturn. In contrast, less massive disks tend to yield smaller, rocky planets. This relationship between disk mass and planet type hints at why different types of planetary systems exist. For instance, many exoplanetary systems feature super-Earths and mini-Neptunes, planets larger than Earth but smaller than Neptune, which don't exist in our solar system. These planetary types might result from disks with moderate amounts of material, either massive enough to create gas giants nor sparse enough to produce only small, rocky planets. Another intriguing element within protoplanetary disks is the concept of the snow line, the region within a disk where temperatures are low enough for volatile compounds, such as water, ammonia, and methane, to freeze into solid ice. The position of the snow line has a profound effect on planet formation. In the inner, hotter regions of a disk, closer to the star, rocky planets are more likely to form because only metals and silicates can condense into solid material. However, beyond the snow line, ice can form, allowing for the accumulation of much more mass and facilitating the development of giant planets with thick, gaseous atmospheres. The position of the snow line also influences the distribution of water and other volatiles within a planetary system, which is crucial for habitability. In our own solar system, Earth resides just within the inner edge of the habitable zone, where liquid water can exist. But in many other systems, planets may form beyond the snow line and migrate inward over time. This migration process could carry ices, organic molecules, and other life-essential compounds toward a star, potentially delivering them to planets that lie within a habitable range. The interplay between the snow line, disk mass, and other factors creates a staggering array of possible planetary configurations. Scientists have observed disks where multiple snow lines exist, indicating regions where various compounds condense at different distances from the star. For example, water, methane, and carbon dioxide each have unique condensation points, so a disk might have separate zones where each of these ices is prevalent. Such a complex structure within a disk could give rise to planets with unique chemical compositions, atmospheres, and surface characteristics. In addition to the diversity of protoplanetary disks, recent research has highlighted the importance of disk turbulence. Within a disk, the movement of gas and dust isn't entirely smooth. There are eddies, vortices, and waves that cause the material to clump together in some areas while dispersing in others. This turbulence can have a major impact on the formation of planets, as clumps of material created by turbulence can serve as the initial seeds, around which larger planetary bodies grow. Turbulence may even help to explain the rapid formation of massive planets in some systems, as it accelerates the accumulation of gas and dust in certain regions of the disk. Observations have shown that turbulence levels vary across different disks, and this variation likely influences the types of planets that form. In regions with intense turbulence, smaller rocky planets might struggle to maintain their orbits, making it harder for them to gather additional material. On the other hand, gas giants may benefit from turbulent regions, as they can quickly gather gas and grow in mass. By studying these variations in turbulence, scientists can gain insight into why certain systems have a higher concentration of gas giants, while others favor smaller, terrestrial planets. In examining protoplanetary disks, scientists also encounter intriguing phenomena such as disk gaps and rings, which appear as bright and dark bands within a disk when viewed with telescopes like ALMA. These gaps and rings are thought to be caused by forming planets, which clear out paths as they orbit within the disk, much like a vacuum cleaner. When a protoplanet moves through the disk, its gravitational influence draws in surrounding material, creating a gap. This process provides direct evidence of planets forming within the disk, giving scientists a snapshot of planet formation in action. Interestingly, disk gaps have been found at various distances from the central star, suggesting that planet formation can occur across a wide range of environments. Some of these gaps appear at distances similar to where Earth orbits the Sun, raising the possibility of Earth-like planets forming in other systems. In some protoplanetary disks, multiple gaps are visible, indicating the presence of several forming planets, each carving out its own orbit and creating a mini-solar system within the disk. Additionally, the study of disk gaps has allowed researchers to identify young planets that are too faint or too close to their parent stars to be seen directly. By analyzing the shapes, positions, and dynamics of these gaps, scientists can estimate the masses and orbits of the planets creating them. This indirect method of detecting planets has become an invaluable tool for discovering new worlds and understanding how planetary systems evolve over time. One remarkable example of this phenomenon is the PDS-70 system, where scientists have observed two young, forming planets within a protoplanetary disk. These planets, each several times more massive than Jupiter, are actively accreting material from the surrounding disk, creating visible gaps in the disk structure. The discovery of these planets has provided a unique opportunity to witness the final stages of planet formation, offering valuable data on how gas giants gather their thick atmospheres and settle into stable orbits. The study of protoplanetary disks also offers insights into the potential formation of planetary rings and moons. As a planet forms within a disk, its gravity captures smaller particles and objects nearby, some of which may end up in stable orbits around the planet. Over time, these captured objects can coalesce into moons, while finer material might form rings. This process, which likely gave rise to the moons and rings of Saturn, Jupiter, and other planets in our solar system, reveals yet another layer of complexity in the development of planetary systems. Moons themselves play an important role in the stability and habitability of planets. In our solar system, Earth's moon has a stabilizing effect on our planet's axial tilt, which helps maintain a relatively stable climate over long periods. Similar dynamics may be at work in other planetary systems, where moons could contribute to the habitability of planets by influencing their orbits, climates, and possibly even their geologic activity. The discovery and analysis of protoplanetary disks have also sparked new questions about the architecture of planetary systems, how planets are arranged in relation to each other and their parent star. Observations show that some systems are packed with planets orbiting very close to their star, while others have planets spread out over vast distances. This variety in system architecture suggests that the distribution of planets within a system may be influenced by a complex set of factors, including the initial conditions of the protoplanetary disk, the timing of planet formation, and the interactions between forming planets. Understanding the arrangement of planets within a system has significant implications for the study of habitability. In tightly packed systems, planets may experience strong gravitational influences from nearby planets, leading to unstable orbits or extreme climatic variations. In contrast, systems with planets spread over larger distances may offer more stable environments for potential life to develop. By studying these diverse architectures, scientists can refine their models of habitability, potentially guiding future searches for Earth-like planets and other systems. The incredible progress in observing and understanding protoplanetary disks has been made possible by advances in telescope technology, such as the use of adaptive optics and interferometry, which allow astronomers to capture highly detailed images of distant star-forming regions. The ALMA array, in particular, has revolutionized our view of these disks, enabling us to see fine details in the dust and gas surrounding young stars. The upcoming James Webb Space Telescope will further enhance our ability to study these disks, providing unparalleled sensitivity and resolution in the infrared spectrum, where much of the action within protoplanetary disks occurs. As our observational capabilities improve, we are likely to uncover even more surprises about the process of planet formation. We may find entirely new types of planets or disk structures, challenge existing theories, and perhaps even witness events that have so far remained hidden from view. Each new discovery brings us closer to a comprehensive understanding of how planets form, evolve, and perhaps become habitable worlds. The quest to understand protoplanetary disks and the birth of planets is not just an academic exercise. It is a fundamental pursuit that touches on some of humanity's oldest questions. By tracing the origins of planets, we explore our own origins, the forces that shaped Earth, and the conditions that allowed life to flourish here. Each protoplanetary disk we observe is a reminder that the universe is full of potential, with countless stars, each possibly nurturing the seeds of its own solar system and perhaps even life. Our journey through protoplanetary disks and planet formation brings us to one of the most profound aspects of cosmic evolution, the role of time. Planet formation within a protoplanetary disk doesn't occur overnight. It's a process spanning millions, sometimes tens of millions of years. During this period, the star itself is still young and often volatile, producing powerful stellar winds and radiation that interact dynamically with the material in the disk. This intricate dance between a young star and its disk, shaped by the influences of time and environment, sculpts each unique planetary system. As a star matures, the energy it radiates begins to erode the surrounding protoplanetary disk. This process, known as photoevaporation, is when high-energy particles from the star's radiation strip away gas and dust, creating gaps and thinning the disk over time. This gradual clearing of the disk places a critical constraint on planet formation. If planets are to fully form, they must gather the necessary material before the star's energy disperses the disk entirely. In many cases, especially for gas giants, if the star clears the disk too soon, a planet may fail to accumulate a thick, gaseous atmosphere and remain as a smaller, rocky world. Interestingly, the age of the star and the lifespan of the disk can vary widely. For low-mass stars, like red dwarfs, disks can last longer, giving planets more time to form and mature, and potentially allowing for more stable, enduring planetary systems. These extended timescales have led scientists to consider red dwarfs as promising candidates in the search for habitable exoplanets, especially since these stars are the most common in our galaxy. In contrast, stars that are much larger and hotter than our Sun, such as massive O-type stars, emit intense radiation that can clear their disks quickly, often within a few million years. The harsh environment around these stars makes planet formation challenging and might explain why fewer planets are found around massive stars compared to their smaller counterparts. Yet, in these rare instances where planets do form around massive stars, they often have characteristics distinct from those found around smaller stars, potentially giving rise to supermassive gas giants, or even unusual compositions due to the intense environment. With ongoing observations, astronomers are finding that planet formation isn't always confined to the disk surrounding a single star. In binary star systems, where two stars orbit each other, each star may have its own disk, or a single, larger disk may orbit both stars. These dynamic environments add a layer of complexity, as the gravitational pull from both stars influences the material within the disk, creating intricate spiral patterns, disk gaps, and other features that challenge planet formation in fascinating ways. The famous system GG Tau A, for example, contains a disk around a binary star pair, and scientists have observed peculiar structures within the disk, indicating how dual-star interactions can shape planetary nurseries in unique ways. Studying protoplanetary disks within binary systems provides insight into the potential for planets to form in environments far different from our solar system, where only one star governs the formation of planets. Researchers have even discovered planets orbiting binary stars, similar to the fictional world of Tatooine from Star Wars, where a planet orbits two suns. These real-life, circumbinary planets face complex gravitational interactions, but their discovery highlights the remarkable adaptability of planetary formation processes. Another aspect influencing planet formation is the composition of the protoplanetary disk itself. Elements heavier than hydrogen and helium, known as metals, in astrophysical terms, play a crucial role in the formation of rocky planets and the core of gas giants. A star and its disk inherit these heavier elements from previous generations of stars that went supernova, dispersing their material into the surrounding space. This cycle of star formation, supernova, and reformation is what enriches regions of the universe with the essential building blocks for rocky planets. Stars born in environments rich in metals have a greater chance of forming planets, especially rocky worlds, since there's more material available for the formation of solid cores. Our Sun, for example, formed in a region of the galaxy with a relatively high metal content, which likely contributed to the development of the rocky planets within our solar system. Observing protoplanetary disks around stars with varying metal content has allowed scientists to identify a correlation between metal-rich disks and a higher likelihood of planet formation, providing a valuable indicator when searching for potentially habitable planets. In addition to metals, organic molecules have been detected within certain protoplanetary disks. These molecules, which contain carbon and are fundamental to life as we know it, suggest that the ingredients for life could be distributed throughout these disks. Discoveries of molecules like methanol, formaldehyde, and even amino acids within protoplanetary disks offer the tantalizing possibility that the earliest stages of life's chemistry may begin even before planets fully form. One intriguing target in the search for organic molecules within disks is the disk surrounding the young star HL Tau, located about 450 light-years from Earth in the constellation Taurus. HL Tau's disk has been observed to contain complex organic compounds, hinting that the foundations of biochemistry could be woven into the very fabric of planet formation. While the presence of organic molecules doesn't guarantee the emergence of life, it does suggest that the building blocks are not unique to Earth and could potentially set the stage for life in diverse planetary systems. Moreover, examining protoplanetary disks can offer clues about the origins of comets and asteroids within planetary systems. Within our solar system, comets and asteroids are thought to be remnants of the early solar nebula, preserving material from the solar system's infancy. Similarly, within protoplanetary disks, leftover material that doesn't coalesce into planets can linger in the form of icy bodies and rocky fragments. These objects may later migrate inward, potentially impacting planets and delivering water and organic materials, as scientists believe occurred with Earth. This late heavy bombardment phase, where young planets are bombarded with leftover material, could be a common phase in planetary system development. By observing disks at various stages of evolution, scientists are beginning to see the potential for these icy bodies to act as delivery systems for water and complex molecules, which could influence the development of habitable conditions on forming planets. Our study of protoplanetary disks, then, not only reveals the mechanisms of planet formation but also hints at the potential for habitability and the origins of life itself. Each new discovery of an organic molecule, or observation of a dust clump forming in a distant disk, brings us closer to understanding the unique set of circumstances that led to life on Earth and the possibilities for life elsewhere. The mysteries of protoplanetary disks and the birth of planets continue to unfold as we push the boundaries of technology and observation. Upcoming missions, such as the James Webb Space Telescope and the planned Extremely Large Telescope, promise to give us a closer look at the intricate details within these disks, enabling us to peer into the cosmic ovens where planets are baked. By focusing on the faint light from young stars and their surrounding material, we're beginning to see the full complexity of the process, from the tiny dust grains that start it all to the majestic planets that emerge from it. Every glimpse into a protoplanetary disk is a step closer to comprehending our place in the cosmos. It reminds us that the forces and processes that created Earth are not unique but part of a universal phenomenon. As we continue to study these enigmatic disks, we may one day find answers to the fundamental question, are we alone, or is the universe teeming with planets like ours, orbiting distant stars, waiting for us to discover them? The mysteries of space, particularly those involving protoplanetary disks, underscore the vastness and complexity of the universe. Each discovery, each breakthrough in understanding, expands our awareness of the dynamic processes that shape solar systems and the potential for life beyond our own. And as we continue our exploration, driven by curiosity and guided by science, we stand at the threshold of answers that may forever change how we view our place in the universe. This vast journey through protoplanetary disks and the formation of planets has revealed the astonishing complexity and beauty of these cosmic nurseries. Each dust particle, gas molecule, and swirling clump of material within these disks represents a potential seed for planets, moons, and entire planetary systems, bringing us closer to understanding how the architecture of the universe is crafted. As our observational techniques evolve, we uncover not only more details about planet formation but also new layers of complexity that hint at the incredible diversity of planetary systems. A fascinating aspect of studying these disks is how they illuminate the conditions under which habitable worlds might emerge. Observations of protoplanetary disks have allowed scientists to see beyond the processes that form planets to the environmental factors that could create stable, life-supporting conditions on these worlds. For example, if a disk contains enough icy bodies, these materials can eventually coalesce into comets and planetesimals, later crashing onto forming rocky planets and potentially delivering essential compounds like water and organics. In systems similar to our own, it's hypothesized that these impacts played a vital role in creating the conditions that allowed Earth to support life. Observations of protoplanetary disks have also raised questions about the boundaries of habitability. The classic, habitable zone, concept, where conditions allow liquid water to exist on a planet's surface, may not be as rigid as once thought. By studying disks with varying distributions of material and environmental factors, astronomers are beginning to understand that certain planets, even if located outside the traditional habitable zone, could still host life. For instance, moons around gas giants within a star's habitable zone could retain atmospheres and even subsurface oceans, expanding the criteria we use to identify potential life-supporting environments. In fact, the diversity in disk composition, structure, and age introduces the possibility that there may be planets whose atmospheres or geological conditions enable habitability in unexpected ways. For example, planets with dense atmospheres might retain enough heat to support liquid water even at a greater distance from their stars. The study of these disks suggests that life-supporting conditions could exist in forms and locations we have yet to fully comprehend, offering new hope in the search for extraterrestrial life. Moreover, as astronomers scrutinize disks around stars of different sizes, they are gaining insights into the potential for planets to retain stable orbits that support life over long periods. Stars with lower mass, such as red dwarfs, often host planets that orbit closer to the star, allowing these planets to exist within the habitable zone without being subjected to extreme gravitational forces that might destabilize their orbits. In these cases, the extended lifespan of red dwarfs, which can shine for tens of billions of years, might give planets a greater window for life to evolve, perhaps making these stars prime candidates in the search for long-term habitability. Additionally, one of the most promising advancements in studying protoplanetary disks is the refinement of direct imaging techniques. Observing distant exoplanets directly remains a challenge due to the blinding brightness of stars, but new technologies and methods are allowing scientists to capture the faint glow of young planets still embedded within their protoplanetary disks. These glimpses allow researchers to analyze the composition and physical conditions of forming planets, yielding details about their atmospheres and potential climates. Using these direct imaging techniques, scientists have been able to observe gaps, rings, and asymmetries within disks. These structural features often serve as clues that planets are forming within these regions, their gravitational influence shaping the disk around them. For example, the star PDS-70, located about 370 light-years away, has a protoplanetary disk where two giant planets have been directly observed. The larger of the two planets, PDS-70b, is enveloped by its own smaller disk of material, hinting at a moon-forming process similar to how our own solar system's moons likely formed around Jupiter and Saturn. The discovery of planetary formation around PDS-70 has been groundbreaking not only for its direct imaging but also for providing a clear view of the diverse environments in which planets might form. The presence of multiple gaps and rings within the disk indicates that these young planets are shaping the disk's evolution. Such detailed observations allow scientists to theorize how these processes might unfold in other planetary systems, shedding light on the range of potential conditions for planet formation. Adding to the complexity is the fact that disks often contain regions with varied chemical compositions and physical properties. For instance, some areas within a disk may be dominated by gas, while others are rich in icy or rocky material, creating distinct chemical zones. These zones influence not only the types of planets that can form but also their characteristics and potential for supporting atmospheres. In the inner regions of a disk, closer to the star, high temperatures can vaporize volatiles like water, meaning that planets formed here are more likely to be rocky. Farther out, where temperatures are cooler, icy and gaseous materials can accumulate, leading to the formation of gas giants, or ice giants. These chemical gradients within disks provide insight into how our solar system's architecture may have emerged. The planets closest to the Sun, Mercury, Venus, Earth, and Mars, are rocky because they formed in a region where temperatures were too high for gas and ices to condense. Meanwhile, the outer planets like Jupiter and Saturn formed in the colder regions, where volatile compounds could remain solid, allowing these giants to accumulate thick atmospheres. Observations of protoplanetary disks around other stars continue to validate this pattern, suggesting that the solar system's structure may not be unique. What makes the study of protoplanetary disks especially exciting is how it bridges the gap between theory and observation. Decades ago, the formation of planets was largely a theoretical pursuit, with scientists piecing together models based on limited data. Now, with high-resolution observations and powerful computational simulations, astronomers can compare their theoretical models with real-world data, validating or revising their ideas. This interplay between observation and theory continues to refine our understanding, allowing scientists to predict what types of planets might form under different conditions. Looking to the future, upcoming advancements in telescope technology promise to revolutionize our view of these early planetary nurseries. Instruments like the Extremely Large Telescope, ELT, in Chile and the planned Habitable Worlds Observatory will allow scientists to observe protoplanetary disks with even greater precision, capturing minute details that remain invisible to current instruments. These next-generation observatories will likely uncover previously hidden structures within disks, revealing how the smallest clumps of dust evolve into full-fledged planets. Equipped with these cutting-edge tools, astronomers will be able to answer fundamental questions about planetary systems. How common are planetary systems like our own? Are there configurations we have yet to imagine? And perhaps most significantly, do other planetary systems hold the potential for life? By mapping and analyzing a vast array of protoplanetary disks, scientists will be able to identify patterns and anomalies that shape the diversity of planetary systems throughout the galaxy. These advancements mark an extraordinary chapter in our understanding of the universe. For centuries, humanity has looked up at the stars, questioning the origins of our world and our place in the cosmos. The study of protoplanetary disks offers an answer grounded in scientific discovery, showing that our planet's birth and the emergence of life were part of a larger cosmic narrative that plays out across billions of stars. The more we learn about protoplanetary disks, the more we see the connections between planet formation and the conditions for life. While Earth may seem like a unique oasis, it is becoming clear that the processes that shaped our world are part of an intricate cosmic cycle, one that has unfolded countless times in countless ways across the universe. Protoplanetary disks, in their quiet, swirling vastness, hold the secrets to that cycle, a mystery waiting to be fully understood. As we continue exploring the mysteries of protoplanetary disks and the origins of planets, we're reminded that every planet, every system, and perhaps even every life form may trace its roots to these swirling clouds of gas and dust. It's a journey that is only just beginning, with each new discovery serving as a testament to the boundless complexity and beauty of the cosmos. As we delve deeper into the mysteries surrounding protoplanetary disks, one of the most intriguing questions centers on the exact mechanics of how planets ultimately clear their orbits, establishing themselves within a stable, long-term position around their host stars. The process of clearing refers to a young planet's ability to sweep up or eject debris within its path, carving out a distinct space in the disk. This phenomenon helps to form the neatly ordered planetary systems we observe, where planets orbit in relatively clean paths, largely free of loose material. The act of clearing is a powerful display of gravitational influence. As a growing planet accumulates mass, it begins to exert a significant gravitational pull on nearby particles and smaller bodies within the protoplanetary disk. Over time, this gravitational influence allows the planet to either attract debris into itself, merging with it and increasing its own mass, or to fling it away, effectively clearing its orbit. This is a key aspect of the transition from a chaotic disk full of colliding particles to a more orderly system where planets hold stable orbits. Interestingly, this clearing process can create gaps or rings within the disk that are observable from Earth. When telescopes reveal rings within a protoplanetary disk, astronomers often interpret these patterns as evidence of planetary formation, with one or more planets likely causing the gaps by exerting their gravitational influence. The discovery of these gaps has allowed scientists to pinpoint the possible locations of developing planets within the disks of distant stars. By examining the structure of these gaps, they can estimate not only the position of these young planets, but also their size and mass based on the width and shape of the cleared region. The rings within these disks are not uniform, and their diversity offers insight into the different types of planets that may form within them. In some disks, we find evidence for the creation of massive gas giants, which exert a powerful gravitational force and thus carve out wider gaps. In other disks, the rings are narrower, suggesting the presence of smaller, rocky planets that have yet to accumulate a significant amount of mass. This variation in ring width and structure across different disks reflects the diversity of planetary systems throughout the galaxy, illustrating that our solar system is just one of countless possible configurations. Beyond gas giants and rocky worlds, the study of protoplanetary disks also opens the door to understanding a broader range of planetary types. In recent years, astronomers have identified super-Earths and mini-Neptunes orbiting stars in our galaxy. Super-Earths are rocky planets larger than Earth but smaller than the ice giants Uranus and Neptune, while mini-Neptunes are smaller gas planets with thick atmospheres. The formation of these exotic planetary types has expanded our understanding of what a planetary system can look like. Super-Earths, in particular, are of great interest because they may possess conditions that support life, with atmospheres thick enough to maintain stable climates yet rocky surfaces suitable for habitation. The diversity of planetary types within protoplanetary disks adds to the broader mystery of why certain disks seem to favor particular kinds of planets. Some disks appear to predominantly form gas giants, while others yield primarily smaller, rocky planets or super-Earths. This preference may be due to a variety of factors, including the amount of gas and dust present, the disk's temperature profile, and the star's luminosity. For instance, stars with stronger radiation fields may disperse the disk's gas more quickly, leaving behind material that favors the formation of rocky planets rather than gas giants. Understanding why certain disks yield specific types of planets remains one of the central challenges in planetary science, with each new discovery providing valuable clues. One fascinating factor in planet formation within protoplanetary disks is the role of magnetic fields. Young stars often possess strong magnetic fields that interact with their surrounding disks, influencing the distribution of material and even the movement of particles within the disk. These magnetic interactions can cause turbulence, which in turn affects how particles collide and stick together. In regions of higher magnetic activity, turbulence may prevent particles from merging, while in calmer regions, particles have a better chance of coalescing into larger bodies. Magnetic fields thus add another layer of complexity to the formation of planets, and studying these interactions continues to be a key area of research. In addition to the formation of planets, protoplanetary disks also play a role in shaping the potential atmospheres of these worlds. The chemical makeup of a disk determines the types of compounds available to a developing planet, influencing whether it will have an atmosphere rich in hydrogen and helium, typical of gas giants, or one composed of heavier molecules like nitrogen, carbon dioxide, or water vapor, more common in rocky planets. The distribution of these compounds within a disk depends on temperature gradients, with different elements and molecules condensing at various distances from the star. For instance, water tends to freeze in the outer regions of the disk, forming ice that can later contribute to the atmospheres of outer planets, or icy moons. As a result, studying the chemical composition of disks offers insight into the atmospheres that forming planets might eventually develop. Recent observations using instruments like ALMA have detected complex organic molecules within certain protoplanetary disks, including methanol, formaldehyde, and even precursors to amino acids. These molecules are essential for life as we know it, and their presence in disks raises the tantalizing possibility that planets forming in such environments could inherit these compounds, potentially giving rise to life-supporting conditions. Moreover, these organic molecules can become embedded within icy bodies that later collide with forming planets, a process similar to what scientists believe happened in our own solar system. The delivery of water and organics to early Earth by comets and asteroids may have been instrumental in creating the conditions necessary for life. If similar processes occur within other protoplanetary disks, it would imply that the chemical building blocks of life are more widespread in the universe than previously thought. The study of protoplanetary disks also deepens our understanding of the processes that prevent or disrupt planet formation. Not every young star with a disk will develop a planetary system. In some cases, strong radiation from nearby massive stars can erode a disk, stripping away the material necessary for planet formation before the process has a chance to complete. This phenomenon is particularly common in densely populated star-forming regions, where massive stars emit intense ultraviolet radiation that ionizes and disperses the gas within surrounding disks. The destruction of protoplanetary disks by neighboring stars serves as a reminder of the fragile balance required for planetary systems to emerge, adding an element of cosmic chance to the formation of worlds. Our observations of protoplanetary disks continue to reveal a dynamic process full of surprises, and as we improve our observational techniques, the details of this process only grow more fascinating. It's not just that disks are forming planets, it's that they're doing so in ways that challenge our assumptions, suggesting a universe where planetary systems are as unique and varied as the stars they orbit. Each disk is a cosmic experiment, governed by universal principles but also shaped by local conditions that produce endlessly diverse outcomes. At its heart, the study of protoplanetary disks and planet formation speaks to one of humanity's oldest questions: where do we come from? By understanding the birth of planets around distant stars, we gain perspective on our own planet's origins and place within the universe. Protoplanetary disks are not just fields of dust and gas. They are the cosmic workshops where planets, atmospheres, and potentially even the conditions for life are forged. The mystery of these disks offers a mirror through which we can view the genesis of worlds, a reminder that our planet's history is part of a much larger cosmic narrative. As scientists push forward with new missions and technological advancements, the study of protoplanetary disks will likely yield even more groundbreaking discoveries. Future telescopes may reveal details we have yet to imagine, offering clarity on questions that today remain unresolved. Will we find universal patterns that dictate how planets and planetary systems form, or will we discover that each system is a unique outcome shaped by its environment? The answers lie within these enigmatic disks, quietly swirling around young stars across the galaxy, holding the secrets of planetary genesis and the mysteries of cosmic evolution. The future of protoplanetary disk research holds exciting possibilities for understanding the forces that give rise to diverse planetary systems. As we stand on the threshold of an era marked by powerful observational tools, we're moving closer to uncovering the intricacies of planet formation processes that have long eluded us. Next-generation telescopes, both in space and on the ground, are designed to explore these disks in greater depth, from their magnetic fields and temperature gradients to their chemical composition and density variations. This closer look at protoplanetary disks is expected to shed light on why certain disks form rocky planets, others gas giants, and still others combinations of both, creating the remarkable diversity of planetary systems in our galaxy. One of the most anticipated advancements in this field comes with the deployment of observatories equipped with advanced imaging capabilities that can capture high-resolution images of distant disks. The James Webb Space Telescope, JWST, launched with the aim of exploring the early universe, also holds incredible potential for studying planetary formation. With its infrared capabilities, JWST can peer through the dense dust clouds surrounding young stars, observing disks at wavelengths that reveal the molecular structures within. Observing the molecular composition, particularly of elements like hydrogen, carbon, oxygen, and nitrogen, can reveal the building blocks of potential atmospheres, offering a preview of the planetary environments that might eventually emerge. The JWST's ability to study water vapor within these disks is especially important. Water is a key indicator of habitability, and understanding its distribution within protoplanetary disks can hint at which regions are more likely to form planets capable of sustaining life. Regions within a disk where water and other volatile compounds condense into ice form what is known as the frost line, or snow line, a critical boundary that determines the types of planets likely to emerge. Inside the frost line, the heat from the central star prevents ice from forming, leading to rocky planets. Beyond it, where water can condense, we're more likely to find gas giants or icy bodies rich in volatile compounds. Mapping the frost lines within different disks around various types of stars could provide clues as to how many planets with water-rich environments might exist in the galaxy. JWST's observations are also poised to answer questions about how planets form within binary or multiple star systems, which make up a substantial fraction of stars in our galaxy. Planet formation within these systems presents unique challenges because the gravitational forces of multiple stars can destabilize a disk, affecting the accumulation of material into planets. Disks in these complex environments often display intricate, distorted structures, with material being periodically perturbed by the gravitational influence of their host stars. Understanding how planets emerge in such unstable disks could reveal the adaptability of planet formation and hint at potential planets within such systems that we may not expect to be habitable, yet possess the conditions for hosting life. Ground-based observatories are also continuing to evolve, taking advantage of adaptive optics and new interferometry techniques to overcome the blurring effects of Earth's atmosphere. The European Southern Observatory's Extremely Large Telescope, ELT, and the 30-meter telescope, TMT, are both expected to revolutionize our view of protoplanetary disks with unprecedented resolution. These observatories will allow us to analyze the distribution of gas, dust, and larger bodies within disks in intricate detail, potentially even capturing images of forming planets within them. With these telescopes, we might directly observe the early stages of planet formation and better understand the gap-clearing process, where young planets carve out pathways in the disk. Another key tool in the study of protoplanetary disks is the method of polarimetry, a technique that measures the polarization of light. Polarized light is light that has been scattered by particles, allowing astronomers to distinguish between different materials within the disk, such as small dust grains and larger solid bodies. Polarimetric studies provide valuable insight into the sizes, shapes, and compositions of particles, helping scientists understand how these particles evolve over time. By observing the gradual transformation of dust particles into larger aggregates, astronomers can track the process by which disks eventually produce planetesimals and, ultimately, planets. While direct observation and advanced imaging tools provide substantial information, the field of computational astrophysics also plays a significant role in studying protoplanetary disks. Computer simulations allow scientists to model the complex physics of disk evolution, including turbulence, magnetic interactions, and chemical reactions. These simulations can test hypotheses about how particles interact within the disk, how planets accrete gas, and how migration affects the final arrangement of planets. As computers grow more powerful, these simulations become increasingly realistic, allowing astronomers to test different disk conditions and predict the types of planetary systems they might produce. Such models are invaluable in bridging the gap between observed data and theoretical understanding. One particularly interesting area of simulation research involves the migration of planets within a disk. As a planet forms, it does not necessarily stay in the same orbit where it first accumulated mass. Instead, interactions with the surrounding gas and dust can cause it to migrate inward or outward, dramatically changing its position within the system. This migration can help explain certain features of observed planetary systems, such as hot Jupiters, gas giants that orbit very close to their stars. These massive planets likely formed further out in the disk, beyond the frost line, where gas giants typically accumulate. Through migration, however, they move closer to their stars, creating an entirely different planetary arrangement. Studying these migration processes gives us insight into the dynamic nature of young planetary systems and how planetary positions can change over time. Moreover, migration has important implications for planetary habitability. If a rocky planet initially forms beyond the frost line and migrates inward, it might carry water ice and other volatiles to a closer, warmer orbit, potentially creating conditions favorable for life. Similarly, migration can lead to unique configurations where gas giants act as gravitational shepherds for smaller, rocky planets, either stabilizing or destabilizing their orbits. The migration of planets is thus a fundamental aspect of system evolution that significantly impacts the potential for life and the structure of the resulting planetary configuration. While the study of protoplanetary disks answers some questions, it inevitably raises new ones, especially when it comes to the origins of life. Observing disks rich in organic molecules suggests that the chemical precursors to life may be common in young planetary systems. But how these ingredients come together to form living organisms remains one of the greatest mysteries. Protoplanetary disks containing organic compounds might form planets with atmospheres capable of supporting complex chemistry, but it is still unclear what conditions are necessary to transform these organic molecules into life itself. Studying the chemistry of protoplanetary disks could provide clues as to how often these conditions arise in the galaxy. As we continue to observe and simulate the formation of planets in these disks, we gain insight not only into the physical processes that shape them but also into the potential diversity of environments where life might emerge. The knowledge that planetary systems with complex, organic-rich environments are not unique to our own solar system suggests that the conditions for life may indeed be widespread. If we are to find life elsewhere in the universe, it may very well be on a planet orbiting a star that began its journey to habitability within a protoplanetary disk much like the ones we study today. The study of protoplanetary disks is a journey into our own cosmic origins, and it remains a vibrant field with much left to explore. Each new discovery builds upon centuries of curiosity, pushing us ever closer to understanding how the universe constructs the intricate environments that lead to planets, atmospheres, and perhaps, life itself. With every new observation and each refined model, we are granted a glimpse into the forces that crafted our solar system and continue to shape worlds across the cosmos. These swirling disks of gas and dust are more than the building blocks of planets. They are the beginning of countless stories yet to be told, mysteries waiting to be uncovered, and potentially, the seeds of life waiting to take root in worlds beyond our own. The mysteries of protoplanetary disks bring us to the forefront of humanity's quest to comprehend the cosmic origins of life and the fabric of planetary systems. These swirling disks of gas and dust represent the earliest stages of planetary birth, and every discovery made within them pulls us further into the awe-inspiring journey of planetary formation. The phenomena observed in protoplanetary disks reveal not only how planets like Earth might have formed but also suggest that the vast number of planets across the cosmos likely emerged in similar ways. One compelling aspect of protoplanetary disks is the role of dust grain coagulation. At first glance, these minuscule grains of dust may seem insignificant. However, their journey from tiny particles to planetesimals, solid objects that serve as the building blocks of planets, involves a sequence of complex physical processes that are still being deciphered. As grains collide, they stick together, creating larger aggregates over time. This process continues until these small aggregates form pebbles, and later, boulders, and eventually, larger bodies capable of influencing their surroundings through gravitational interactions. Each of these steps toward planetary formation relies on a delicate balance of physical forces, including gravity, electrostatic attraction, and turbulence, which allows these dust grains to grow without breaking apart due to high-impact collisions. A key process that facilitates planetesimal formation within protoplanetary disks is the mechanism known as streaming instability. In a protoplanetary disk, gas rotates at a slightly slower speed than dust due to the pressure gradient from the central star's gravity. This difference in velocity causes dust grains to clump together as they try to move faster than the gas. Streaming instability creates localized regions of increased dust density, eventually leading to the formation of planetesimals and what is essentially a cosmic snowball effect. This discovery has been crucial for understanding how solid bodies form in regions where turbulence would otherwise disperse the particles, highlighting the resilience and adaptability of planet formation processes within these turbulent disks. Furthermore, recent research suggests that magnetic fields may play a pivotal role in shaping protoplanetary disks and influencing the formation of planets. Magnetic fields can generate powerful forces within the gas and dust, affecting the movement of particles in ways that promote both dust aggregation and disk accretion. These magnetic interactions can also create dead zones within the disk, areas where the turbulence is significantly reduced, allowing dust to settle and coagulate without being disrupted by chaotic gas flows. The existence of dead zones may be critical to understanding why certain disks yield massive planets, while others produce more diminutive, rocky worlds. The dynamics within these magnetic regions provide insight into the diverse range of planetary architectures observed across different systems. Temperature gradients within protoplanetary disks also have profound effects on planetary formation. The proximity to the central star determines the thermal environment in different parts of the disk, with the inner regions reaching extreme temperatures while the outer regions remain frigid. This temperature variance is crucial in determining the type of materials that can condense into solids at each distance from the star. Closer to the star, only metals and rocks remain solid, leading to the formation of terrestrial planets like Earth. In contrast, further out, cooler temperatures allow for the condensation of ices and volatile compounds, which are essential for forming gas giants and icy bodies. This temperature-based distribution within the disk, along with the frost line, not only dictates the types of planets that can form but also impacts the potential for life on these planets by influencing their compositions and atmospheres. The interplay of gas, dust, and planetesimals within a disk gives rise to complex structures that can be observed in remarkable detail with modern telescopes. Observations have revealed a variety of ring structures, gaps, and spirals within protoplanetary disks, which are thought to be the gravitational influence of forming planets carving paths through the disk. The gap clearing process seen in many protoplanetary disks serves as indirect evidence of planets, allowing scientists to infer the presence and size of young planets even before they become observable directly. Each gap tells a story about the planetary body that created it, its mass, its potential composition, and its orbital path around the central star. By mapping these gaps, astronomers can reconstruct the architecture of nascent planetary systems, offering a rare glimpse into the developmental stages of planets. Spirals within disks, another intriguing feature observed, are often caused by gravitational interactions with nearby stars or by massive planets stirring up the disk's gas and dust. These spirals can transport material from one region of the disk to another, contributing to the redistribution of elements and compounds necessary for planet formation. The structure of these spirals provides clues about the forces shaping the disk and offers insight into how material flow affects the formation of various planetary bodies. As we uncover more examples of spiral structures, we are beginning to understand how each protoplanetary disk's unique configuration influences the types of planets that may emerge from it. The study of protoplanetary disks is continuously expanded through the use of sophisticated computer simulations that allow scientists to model various scenarios of disk evolution. By inputting parameters like mass, temperature, gas density, and particle size, astrophysicists can observe how different conditions affect the formation of planets. These simulations, based on data from telescopic observations, enable scientists to test hypotheses about planet formation and explore the conditions under which different types of planets arise. Each simulation offers a window into the mechanisms that underlie disk dynamics, providing theoretical models that can then be tested through direct observation. One of the fascinating revelations from simulations involves the process of core accretion, as it applies to gas giant formation. Core accretion suggests that gas giants begin with a solid core that reaches a critical mass, enabling it to accumulate vast amounts of gas from the surrounding disk. This process occurs most effectively in regions beyond the frost line, where icy and rocky materials are abundant. By examining the role of core accretion, scientists gain a deeper understanding of how our own solar system's gas giants, such as Jupiter and Saturn, may have formed. This model also helps explain the diversity of gas giant sizes and compositions observed in exoplanetary systems. Another crucial discovery made possible by simulations is the concept of disk instability, a process that occurs in massive, turbulent disks with high densities. Unlike core accretion, disk instability allows gas giants to form more quickly by directly collapsing regions of the disk into massive planetary bodies. Disk instability is thought to account for the formation of particularly massive gas giants or brown dwarfs, especially in young, dense systems. Understanding when and where disk instability might occur enables scientists to refine their models of planetary formation, predicting which systems might contain particularly large and unique planets. Each of these findings adds depth to our understanding of protoplanetary disks and the myriad ways they give rise to planets. Through continuous observation, simulation, and theory building, we are piecing together the cosmic puzzle of planetary formation. Every insight into protoplanetary disks helps astronomers envision the environments that shape not only individual planets, but also the entire planetary systems that orbit young stars. The pursuit of answers in the realm of protoplanetary disks remains an inspiring journey, with new discoveries appearing at a rapid pace. The future promises even more revelations as advanced telescopes, such as the Giant Magellan Telescope and the Square Kilometre Array, come online. These instruments are expected to delve into protoplanetary disks with a level of detail unimaginable a few decades ago, potentially capturing images of young planets as they form within the gas and dust. Each observation brings us closer to understanding our place in the cosmos, tracing the path from primordial dust to worlds capable of sustaining life. Ultimately, protoplanetary disks hold the key to many of the universe's enduring mysteries. They reveal the delicate balance of forces that give rise to planets, offer clues about the potential for life on other worlds, and provide a profound understanding of the processes that crafted our solar system. By studying these remarkable disks, humanity continues its timeless journey to explore, understand, and find meaning in the stars above. The secrets of protoplanetary disks, once unlocked, could change our view of the universe forever, offering insights not only into the cosmos but also into the very origins of life itself. As we continue our exploration of protoplanetary disks and the birth of planets, it's essential to delve deeper into the various types of planetary bodies that emerge from these fascinating cosmic structures. The diversity of planets we observe across the universe can be attributed to the myriad conditions found in protoplanetary disks, as well as the physical processes that govern their formation. Types of planets formed in protoplanetary disks. The planets that emerge from protoplanetary disks can be broadly categorized into terrestrial planets, gas giants, ice giants, and a variety of other bodies such as dwarf planets and exoplanets. Each category represents distinct characteristics based on their composition, formation processes, and locations within the disk. 1. Terrestrial planets. These rocky worlds, including Earth, Mars, Venus, and Mercury, form close to the central star where the temperature is high enough to prevent volatile substances like water and gases from condensing into solid form. The materials available in these inner regions are primarily silicates and metals. During the planet formation process, repeated collisions between smaller planetesimals lead to the gradual accumulation of mass, creating larger bodies that eventually coalesce into fully formed planets. The dynamics of accretion and the availability of materials play crucial roles in the final size and composition of terrestrial planets. 2. Gas giants. Found in the outer regions of protoplanetary disks, gas giants like Jupiter and Saturn are formed from a solid core that accumulates gas from the surrounding disk once it reaches a certain critical mass. This critical mass allows them to attract and retain massive envelopes of hydrogen and helium, forming the gigantic, thick atmospheres characteristic of gas giants. The unique formation mechanisms of gas giants can also lead to variations in their compositions and atmospheric structures, often influenced by the initial conditions of the protoplanetary disk. Gas giants typically have multiple moons and may have ring systems formed from debris captured by their gravitational pull. 3. Ice giants. Uranus and Neptune represent the category of ice giants, which lie between terrestrial planets and gas giants. They are primarily composed of ices, such as water, ammonia, and methane, in addition to rock and gas. Ice giants tend to form in the outer reaches of the protoplanetary disk, where the temperatures allow for the condensation of these volatile materials. Their unique formation processes often lead to different internal structures compared to gas giants, including higher densities and distinct atmospheric compositions. 4. Dwarf planets and exoplanets. Dwarf planets, such as Pluto and Eris, are smaller bodies that did not clear their orbital zones of debris. They typically share similarities with terrestrial planets and can exist in both inner and outer regions of protoplanetary disks. Exoplanets, or planets beyond our solar system, represent a vast and diverse array of worlds that can vary dramatically in size, composition, and atmosphere. Observing protoplanetary disks helps scientists understand the potential for exoplanets to form and evolve over time, contributing to our knowledge of planetary systems throughout the universe. Observational techniques and their impact on understanding protoplanetary disks. As we expand our understanding of the various planetary types formed in protoplanetary disks, we must also consider the technologies and techniques that allow us to observe these disks and gain insights into their structure and dynamics. The development of advanced observational tools has revolutionized our ability to study protoplanetary disks in unprecedented detail. 1. Interferometry. One of the most significant advancements in observational astronomy is the use of interferometry, which allows astronomers to combine data from multiple telescopes to create high-resolution images of protoplanetary disks. Instruments like the Atacama Large Millimeter/Submillimeter Array, ALMA, have made groundbreaking observations of disks, revealing their complex structures and dynamics. Through interferometry, researchers can detect the distribution of gas and dust, identify gaps created by forming planets, and even map the temperature variations within the disk. 2. Spectroscopy. Spectroscopy plays a critical role in understanding the chemical composition of protoplanetary disks. By analyzing the light emitted or absorbed by materials within the disk, scientists can identify the presence of various molecules, such as carbon monoxide, water, and organic compounds. These observations help establish the chemical inventory available for planet formation, shedding light on the potential for life-sustaining elements to exist on newly formed worlds. 3. Direct imaging. While direct imaging of planets within protoplanetary disks is challenging due to the brightness of the surrounding gas and dust, advances in imaging techniques have allowed astronomers to capture images of young planets in their formative stages. These images provide invaluable information about the physical characteristics and compositions of forming planets, helping scientists refine their models of planetary development. 4. Polarimetry. This technique measures the polarization of light scattered by dust grains in protoplanetary disks. By studying the polarization patterns, astronomers can infer information about the sizes, shapes, and spatial distributions of dust particles within the disk. Polarimetry offers insights into the dust growth processes that contribute to planet formation and allows for a better understanding of the disk's overall structure. The significance of protoplanetary disk studies in astrobiology. The study of protoplanetary disks extends beyond the realm of planetary formation. It also holds significant implications for the field of astrobiology. Understanding how planets form and the materials available to them provides crucial context for exploring the potential for life elsewhere in the universe. 1. Habitability. The composition and arrangement of materials in a protoplanetary disk influence the potential habitability of the resulting planets. Terrestrial planets formed in the habitable zone, where conditions allow for liquid water to exist, are prime candidates for hosting life. By analyzing the ingredients available in disks, scientists can assess the likelihood of life-sustaining environments emerging on newly formed planets. 2. Organic compounds. The presence of organic molecules in protoplanetary disks raises intriguing questions about the origins of life. Many complex organic compounds have been detected in these disks, suggesting that the building blocks of life may be synthesized in these environments before being delivered to forming planets. Understanding how these organic materials are created and distributed is crucial for exploring the potential for life to arise on exoplanets. 3. Planetary migration. The study of protoplanetary disks also reveals insights into planetary migration, the phenomenon where planets change their orbits over time. Understanding the mechanisms driving migration can help scientists predict the potential for habitable zones to shift and evolve, providing essential context for the long-term stability of planetary systems. 4. Planetary diversity. The diverse range of planetary systems observed in the universe can be partly explained by the varied conditions found in protoplanetary disks. By studying how disks differ from one another, astronomers can better understand the factors that influence the architecture of planetary systems. This knowledge is crucial for exploring the potential for life in the universe, as different planetary arrangements may lead to varying degrees of habitability. Future directions in protoplanetary disk research. As we look toward the future, the study of protoplanetary disks is poised to benefit from continued advancements in technology and observational techniques. Several promising areas of research will likely shape our understanding of planetary formation in the coming years. 1. Next-generation telescopes. The James Webb Space Telescope, JWST, has already begun its mission to observe protoplanetary disks with unprecedented sensitivity and detail. With its ability to capture infrared wavelengths, JWST can penetrate dust and gas, allowing scientists to study the inner regions of disks and observe young stars in the early stages of their formation. The insights gained from JWST will undoubtedly enhance our understanding of protoplanetary disks and the dynamics of planetary formation. 2. Interdisciplinary approaches, combining data from various fields, such as planetary science, astrophysics, and chemistry, will lead to a more comprehensive understanding of protoplanetary disks. Collaborations among researchers from different disciplines can provide valuable insights into the physical processes involved in planet formation and the implications for astrobiology. 3. The search for exoplanets. As technology advances, the search for exoplanets continues to expand. Observations of protoplanetary disks will aid in identifying potential habitable zones and characterizing the conditions under which planets form. The data collected can inform future missions aimed at directly studying exoplanets and their atmospheres, furthering our understanding of planetary systems. 4. Long-term monitoring. Protoplanetary disks evolve over time, and long-term monitoring of these disks will be crucial for understanding the processes that govern their evolution. By observing disks over extended periods, scientists can capture the dynamic interactions that shape the formation of planets and other bodies within the disk. The mysteries of protoplanetary disks are vast and captivating, offering profound insights into the processes that lead to the birth of planets. As we unlock the secrets of these dynamic structures, we gain not only knowledge about our own solar system but also a deeper appreciation for the complex tapestry of planetary systems throughout the universe. The interplay of gas, dust, and gravity within protoplanetary disks reveals the delicate dance of creation, where each speck of material contributes to the formation of worlds that may one day host life. The journey of exploration continues, as astronomers and scientists strive to piece together the puzzle of planetary formation, driven by an insatiable curiosity about the cosmos and our place within it. As we peer into the heart of protoplanetary disks and witness the birth of planets, we are reminded of the beauty and complexity of the universe, igniting our imagination and inspiring future generations to reach for the stars. Through the lens of science and observation, we embrace the mysteries of protoplanetary disks, celebrating the remarkable story of how planets are born and the intricate dynamics that govern their formation. As we immerse ourselves in the study of protoplanetary disks, we also confront intriguing questions about the long-term evolution of these systems. How do planets interact with each other over astronomical timescales? What fates await them as they mature? The life cycle of a planetary system is as complex and diverse as the disks from which they originate. Planetary interactions and system evolution. The interactions among planets and other celestial bodies within a protoplanetary disk play a significant role in shaping the architecture of planetary systems. As planets form, they exert gravitational influences on one another, leading to various dynamic outcomes that can profoundly alter their orbits and characteristics. 1. Planetary migration. One of the most critical processes in the evolution of planetary systems is planetary migration. As planets form and gain mass, they can interact with the surrounding disk material. This interaction can result in changes to their orbits, causing them to migrate inward or outward. For example, gas giants often experience a process known as Type 2 migration, where their gravitational pull clears a path through the disk, causing them to spiral inward toward the star. This migration can significantly impact the stability and arrangement of the planetary system, potentially leading to configurations where gas giants occupy closed-in orbits, much different from the layout seen in our own solar system. 2. Resonances. gravitational interactions between planets can lead to resonant configurations, where the orbital periods of two or more planets are related by a simple ratio. These resonances can enhance stability or cause planets to scatter into different orbits, influencing the evolution of the system. For example, the Laplace resonance observed among Jupiter's moons Io, Europa, and Ganymede demonstrates how such gravitational interactions can lock moons into stable orbits while also driving geological activity through tidal forces. 3. Collisions and mergers. During the early stages of planetary formation, the likelihood of collisions between planetesimals and forming planets is high. These collisions can lead to the growth of larger bodies or, conversely, can result in fragmentation. The process of giant impacts is particularly significant in the history of our solar system, as it is believed that the Moon formed from debris generated by a colossal collision between the early Earth and a Mars-sized body known as Theia. Understanding these collision dynamics provides insights into how planets can gain mass and how their surface conditions can change dramatically. 4. The role of stellar evolution. As stars evolve, they also impact the planets orbiting them. For instance, as a star exhausts its nuclear fuel and enters the red giant phase, it will shed its outer layers, drastically altering the environment for the inner planets. Some planets may be engulfed, while others may find themselves in radically changed orbits. Understanding the life cycle of stars and their influence on surrounding planetary bodies helps us appreciate the fate of planetary systems over cosmic timescales. Observational advances, probing the birth of planets. The future of protoplanetary disk research is bright, fueled by technological advancements in observational capabilities. Several upcoming missions and projects are expected to revolutionize our understanding of how planets form and evolve within these enigmatic disks. 1. Next-generation space telescopes. Following the successful launch of the James Webb Space Telescope, future missions, such as the European Space Agency's Ariel mission, aim to study the atmospheres of exoplanets and their chemical compositions. These missions will provide a wealth of data that can be correlated with observations of protoplanetary disks, offering insights into the conditions that may lead to the formation of habitable environments. 2. Planetary system surveys. Large-scale surveys of protoplanetary disks and exoplanetary systems are expected to provide comprehensive datasets that can be analyzed for patterns and correlations. Projects like the Transiting Exoplanet Survey Satellite, TESS, and the upcoming Roman Space Telescope will help build a more complete picture of the diversity of planetary systems and the mechanisms that govern their formation and evolution. 3. Direct imaging techniques. As mentioned previously, direct imaging of forming planets remains a challenging yet rewarding endeavor. Continued advancements in adaptive optics and coronagraphy will allow astronomers to capture clearer images of planets within protoplanetary disks. The ability to directly observe planets in their early stages will offer invaluable insights into their compositions, atmospheres, and potential for habitability. 4. Laboratory simulations and modeling. Complementing observational efforts, advances in computational astrophysics allow researchers to simulate the dynamics of protoplanetary disks and planet formation processes. By creating sophisticated models that incorporate various physical conditions, astronomers can explore different scenarios of planet formation, migration, and evolution. These simulations can help reconcile observational data with theoretical predictions, providing a more cohesive understanding of the processes at play. The broader implications of protoplanetary disk research. The study of protoplanetary disks is not solely confined to understanding the mechanics of planet formation. It has broader implications for our understanding of the universe. The discoveries made in this field can contribute to several key areas of research. 1. Astrobiology and the search for life. By understanding how planets form and the conditions that influence their habitability, scientists can refine their criteria for identifying potentially habitable exoplanets. The knowledge gained from protoplanetary disk studies can inform the search for life beyond our solar system, guiding future missions aimed at characterizing the atmospheres and compositions of exoplanets. 2. Cosmic evolution. The processes that lead to planet formation are intertwined with the evolution of galaxies. Protoplanetary disks serve as a window into the mechanisms that govern star and planet formation on a cosmic scale. Studying these disks can enhance our understanding of how galaxies evolve and how the elements necessary for life are distributed throughout the universe. 3. Planetary system diversity. The diversity of planetary systems observed in our galaxy highlights the complexity of the processes that shape them. Understanding the range of conditions under which planets can form provides crucial insights into the potential for different types of planetary environments to exist. This knowledge can inform our models of planetary formation, allowing for a more comprehensive picture of the universe's architecture. 4. The future of humanity. As we continue to learn about the formation and evolution of planetary systems, we may uncover new opportunities for exploration and potential colonization beyond our own planet. Understanding the processes that shape planets informs our quest for knowledge about our own solar system, as well as our aspirations for future space exploration. The study of protoplanetary disks and the birth of planets represents a captivating journey into the heart of the cosmos. The intricate interplay of gas, dust, and gravity within these disks gives rise to a diverse array of planetary bodies, each with its own unique characteristics and potential for hosting life. As we continue to unravel the mysteries of these celestial structures, we gain not only insights into our own solar system's history, but also a deeper appreciation for the complexity and beauty of the universe. The ongoing research into protoplanetary disks, fueled by advancements in observational techniques and theoretical modeling, promises to illuminate the processes that shape planetary systems, offering a glimpse into the origins of the worlds that might harbor life. The quest for knowledge in this field is far from over. Each discovery unveils new questions and avenues for exploration, reminding us that the cosmos is an ever-evolving tapestry of wonders waiting to be understood. As we gaze at the stars and ponder our place within the universe, the story of protoplanetary disks and the birth of planets inspires a sense of wonder and curiosity that transcends generations, inviting all of us to participate in the grand exploration of the cosmos. One that echoes through the ages, beckoning future generations to continue this remarkable journey of discovery. As we delve deeper into the nature of protoplanetary disks, it's essential to reflect on how the collective knowledge we gain enriches our understanding of not only planetary formation but also the broader universe. We can view the universe as a grand laboratory in which the laws of physics operate on a cosmic scale, revealing the fundamental principles governing matter, energy, and their interactions. Interdisciplinary connections in astrophysics. The study of protoplanetary disks also exemplifies the importance of interdisciplinary approaches in modern science. Insights from fields such as chemistry, physics, geology, and even biology play a crucial role in our understanding of how planets form and evolve. This interconnectedness underscores the value of collaboration among scientists from various disciplines, leading to a more holistic view of planetary formation and the conditions necessary for life. 1. Astrochemistry. The chemistry within protoplanetary disks is fundamental to understanding the building blocks of planets and potential life. Molecules formed in these environments can lead to the creation of complex organic compounds, which are vital for life as we know it. By studying the chemical processes that occur in disks, scientists can determine the availability of essential elements and compounds that may play a role in the development of life on planets. 2. Planetary geology. The geological characteristics of planets offer insights into their histories and the processes that shape their surfaces. By comparing the geological features of planets formed in similar environments, researchers can draw conclusions about the conditions that led to their formation. For instance, examining the geological history of rocky planets like Mars can shed light on the conditions that prevailed in the early solar system and inform our understanding of habitability. 3. Exoplanetary science. The study of protoplanetary disks is closely tied to the growing field of exoplanetary science. As astronomers discover and characterize new exoplanets, the insights gained from protoplanetary disk research can inform models of how these planets formed. Understanding the initial conditions of planet formation helps scientists develop better techniques for detecting and analyzing exoplanets, ultimately enhancing our knowledge of planetary systems beyond our own. 4. theoretical physics and computational astrophysics. Advanced modeling and simulation techniques are essential tools in the study of protoplanetary disks. Researchers utilize computational astrophysics to simulate various scenarios of planet formation and migration, enabling them to predict the outcomes of complex gravitational interactions. These simulations serve as a testing ground for theories and allow for a deeper understanding of the processes that govern planetary systems. The role of citizen science. The excitement surrounding protoplanetary disk research also extends to the public, where citizen science initiatives provide opportunities for enthusiasts to contribute to scientific discoveries. Projects like Planet Hunters and Zooniverse allow volunteers to assist in analyzing astronomical data, including images of protoplanetary disks and the identification of exoplanets. These initiatives democratize science, engaging the broader community in the exploration of the cosmos and fostering a sense of ownership in the quest for knowledge. Cultural impact and the human experience. The study of planets and protoplanetary disks has profound implications for our cultural understanding and philosophical perspectives. Throughout history, humanity has gazed at the stars, contemplating our place in the universe and our connection to the cosmos. The pursuit of knowledge about planets and their formation evokes fundamental questions about existence, the nature of life, and our relationship with the universe. 1. Philosophical reflections. The exploration of protoplanetary disks raises philosophical inquiries about the nature of existence. What does it mean for a planet to be habitable? How do we define life? These questions are central to the field of astrobiology and challenge our understanding of what it means to exist in the universe. As we uncover the conditions necessary for life, we are compelled to reconsider our assumptions about the uniqueness of Earth and the potential for life elsewhere. 2. Art and inspiration. The mysteries of protoplanetary disks and the birth of planets inspire artists, writers, and creators across disciplines. The imagery associated with these celestial phenomena finds its way into literature, visual arts, and even music. The awe and wonder evoked by the cosmos resonate with the human experience, encouraging us to imagine and explore beyond our immediate reality. 3. Education and outreach. Educating the next generation about the mysteries of space and planetary formation is crucial for inspiring future scientists and thinkers. Programs that engage students in hands-on learning about protoplanetary disks, planets, and the universe as a whole help nurture curiosity and critical thinking skills. By fostering a love for science, we empower young minds to explore the unknown and contribute to humanity's understanding of the cosmos. Future directions in protoplanetary disk research. As we look ahead, several exciting avenues for research and exploration await us in the realm of protoplanetary disks and planetary formation. Technological advancements and ongoing missions will undoubtedly enhance our understanding of these celestial phenomena, leading to new discoveries and insights. 1. Next-generation observatories. The future of astronomical observation lies in the development of next-generation observatories that will enable us to study protoplanetary disks with unprecedented detail. Instruments such as the Extremely Large Telescope, ELT, and the Atacama Large Millimeter/Submillimeter Array, ALMA, will push the boundaries of our observational capabilities, allowing us to resolve fine details of disks and track the formation of planets in real time. 2. Exploration of protoplanetary disks around diverse stellar types. While much of our knowledge comes from studying disks around sun-like stars, a comprehensive understanding of planet formation requires examining a wider variety of stellar environments. Investigating disks around different types of stars, such as red dwarfs or massive stars, will provide insights into how various stellar properties influence the formation and evolution of planetary systems. 3. Investigating the role of magnetic fields. Magnetic fields play a crucial role in the dynamics of protoplanetary disks. Understanding how these fields influence the behavior of gas and dust, as well as their impact on planet formation, represents a significant frontier in research. Future studies will explore the interactions between magnetic fields and the materials within disks, shedding light on the complexities of planetary formation. 4. Studying disk chemistry and organic compounds. The chemistry within protoplanetary disks is fundamental to understanding the building blocks of life. Continued investigation into the organic compounds formed in these environments will enhance our understanding of how life's ingredients are distributed throughout the universe. This research could reveal the potential for life in diverse planetary systems. 5. Simulating planetary formation in extreme conditions. As scientists push the boundaries of computational modeling, simulations of planetary formation in extreme conditions, such as those found in disks around binary star systems or in environments with intense radiation, will deepen our understanding of the diversity of planetary systems. These simulations will provide insights into the formation of unusual planetary types that challenge traditional models. 6. The search for planetary systems beyond our own. The exploration of protoplanetary disks is intricately tied to the search for exoplanets and the understanding of their atmospheres. Future missions dedicated to studying exoplanets will enhance our ability to characterize their potential for habitability, expanding our knowledge of the universe's rich tapestry of planetary systems. The study of protoplanetary disks and the birth of planets represents a fascinating journey that extends far beyond the confines of our solar system. As we unravel the mysteries of these cosmic structures, we gain insights not only into the processes that shape planetary systems, but also into our own place within the universe. The future of this field is bright, driven by technological advancements and the collective curiosity of humanity. Each discovery contributes to a growing body of knowledge that inspires wonder and fuels our desire to explore. The narrative of protoplanetary disks is one of complexity, diversity, and endless possibilities, reminding us that the universe holds secrets yet to be unveiled. As we continue to gaze into the cosmos, let us embrace the spirit of inquiry that has propelled humanity forward for millennia. The birth of planets within protoplanetary disks is just one chapter in the grand narrative of the universe, and each new finding opens the door to further questions, challenges, and discoveries. The pursuit of knowledge is a journey without end, a cosmic odyssey that beckons us to explore, to question, and to marvel at the wonders of the universe that surround us. As we further immerse ourselves in the complexities of protoplanetary disks and the processes leading to planet formation, it becomes increasingly evident that this field of study is not only about understanding how planets come into being but also about deciphering the fundamental nature of our universe. These disks, often teeming with intricate dynamics, provide a glimpse into the formative years of planetary systems, and through their study, we can gain insights into our own solar system's history. The formation of planets from protoplanetary disks involves several key stages, each contributing to the unique characteristics of the planets that eventually emerge. The initial phase begins with the collapse of a molecular cloud, triggered by gravitational instabilities. As this cloud collapses, it forms a rotating disk of gas and dust around a newly formed star. This process, known as the conservation of angular momentum, ensures that material remains in orbit around the central star, gradually leading to the creation of the protoplanetary disk. Within this disk, dust particles collide and stick together, forming larger aggregates in a process known as accretion. This stage is critical, as it sets the foundation for the formation of planetesimals, solid objects ranging from a few kilometers to hundreds of kilometers in diameter. These planetesimals can further collide and merge, eventually growing into protoplanets. The interactions among these objects, governed by gravitational forces, are complex and can lead to diverse outcomes. Some protoplanets will become full-fledged planets, while others may be ejected from the system or remain as smaller bodies, contributing to the asteroid or Kuiper belts. As we examine the characteristics of planets that emerge from protoplanetary disks, we encounter a fascinating diversity. Planets are generally categorized into two main types: terrestrial, rocky, and giant gaseous. Terrestrial planets, like Earth, Mars, Venus, and Mercury, form closer to the star, where temperatures are high enough to prevent significant amounts of gas from condensing. This results in rocky compositions, dominated by silicate minerals and metals. In contrast, giant planets, such as Jupiter and Saturn, form in the cooler outer regions of the protoplanetary disk. Here, hydrogen and helium can condense into ice and gas, allowing these planets to grow massive enough to retain thick atmospheres. The presence of icy materials, such as water, ammonia, and methane, contributes to the distinctive characteristics of these giants. Their formation process can also include a stage of gas accretion, where they gather substantial amounts of gas from the surrounding disk, leading to their enormous sizes. The study of protoplanetary disks is instrumental for understanding not only our solar system but also the myriad of planetary systems that populate the universe. Observations of disks around distant stars have revealed significant variability in their structures and compositions. Some disks exhibit clear gaps, indicative of the presence of forming planets that gravitationally clear their orbits. Others show spiral patterns, which may result from interactions with nearby stars or the gravitational influence of large bodies. Moreover, the chemistry of protoplanetary disks provides essential clues about the potential for habitability in other planetary systems. The presence of organic molecules and water ice within these disks suggests that the building blocks of life may be more widespread than previously thought. Scientists have detected complex organic compounds, including amino acids and sugars, in protoplanetary disks, raising intriguing possibilities about the origins of life in the universe. Understanding the distribution and evolution of these compounds within disks is critical for assessing the likelihood of life elsewhere. The advancements in observational technology, particularly through facilities like ALMA and the James Webb Space Telescope, have revolutionized our ability to study protoplanetary disks in detail. These instruments allow astronomers to observe the thermal emissions and spectral lines of dust and gas within the disks, providing insights into their compositions and structures. By analyzing these emissions, researchers can infer the processes occurring within the disks and track the evolution of material as it transitions from gas to solid form. One of the most captivating aspects of protoplanetary disks is their dynamic nature. These disks do not remain static; they evolve over time, driven by various processes, including turbulence, magnetic fields, and radiative effects from the central star. The interplay between these forces shapes the disk's morphology and influences the efficiency of planet formation. For example, turbulence can enhance the rate of accretion by promoting collisions among particles, while magnetic fields can create outflows that carry away angular momentum, allowing material to settle toward the star. In addition to these physical processes, the timing of planet formation is crucial. The lifespan of a protoplanetary disk can vary significantly, often lasting several million years. During this time, the conditions within the disk change, and the availability of material for planet formation fluctuates. As the disk dissipates, planets may form at different stages, leading to the diverse architectures observed in exoplanetary systems. Some systems feature tightly packed inner planets, while others have distant gas giants orbiting far from their stars. Understanding the timing and processes governing planet formation is essential for unraveling the diversity of planetary systems across the galaxy. The discovery of protoplanetary disks around young stars has also revealed the possibility of multiple generations of planet formation. In some cases, the remnants of earlier disks can contribute to the material found in later disks, leading to complex evolutionary histories. This finding challenges our understanding of planetary formation as a singular event and opens the door to exploring the potential for repeated cycles of planet formation in different environments. As scientists continue to explore the intricacies of protoplanetary disks, they are also increasingly focused on the potential for habitability in exoplanetary systems. The characteristics of a planet's formation, including its distance from the star, the types of materials available, and the conditions within the protoplanetary disk, play significant roles in determining whether a planet can support life. By studying disks around stars of varying masses and ages, researchers can develop models to predict the likelihood of habitable conditions on planets within those systems. The implications of this research extend beyond our solar system and challenge our understanding of life in the universe. As we identify exoplanets in the habitable zone of their stars, where conditions may be suitable for liquid water, we are compelled to consider the broader context of life's potential in diverse environments. The discovery of Earth-like exoplanets in protoplanetary disks opens new avenues for understanding how life may emerge in different cosmic settings. Looking toward the future, the study of protoplanetary disks and planet formation is poised for exciting advancements. The integration of machine learning and artificial intelligence into astronomical research holds the promise of uncovering hidden patterns in vast datasets, allowing researchers to make new discoveries at an unprecedented pace. By applying these techniques to observational data from protoplanetary disks, scientists can enhance their understanding of disk dynamics, planetesimal formation, and the overall evolution of planetary systems. Furthermore, ongoing missions designed to directly image exoplanets will contribute to our understanding of the environments in which they formed. Instruments capable of isolating the light from exoplanets against the backdrop of their host stars will enable astronomers to analyze their atmospheres and surface conditions, providing critical information about their habitability. The interplay between observational astronomy, theoretical modeling, and interdisciplinary collaboration will continue to drive the field forward. By uniting experts from various scientific backgrounds, we can develop comprehensive models that account for the complexities of protoplanetary disks, planetary formation, and the potential for life beyond Earth. Ultimately, the study of protoplanetary disks and the birth of planets is more than a scientific inquiry. It is a quest for understanding our place in the cosmos. As we explore the origins of planets, we gain insights into the broader questions of existence, the nature of life, and the interconnectedness of all things. The mysteries of protoplanetary disks invite us to contemplate the processes that shaped our own world and the myriad possibilities that lie beyond. In this vast universe, where countless stars give rise to planetary systems, the quest for knowledge remains unending. Each discovery adds another layer to our understanding of the cosmic tapestry, reminding us of the beauty and complexity inherent in the processes that govern the formation of planets. As we continue to observe, explore, and theorize, we embark on a journey that not only enhances our scientific knowledge but also deepens our appreciation for the wonders of the universe that inspire us all. The future of planetary science holds great promise, and as we unravel the mysteries of protoplanetary disks, we open new doors to understanding not just the birth of planets, but the potential for life in the cosmos. The stories embedded within these celestial structures resonate with the fundamental questions that define the human experience. Where do we come from? Are we alone? What lies beyond our small blue planet? With each advancement in our understanding, we move one step closer to answering these profound questions and embracing the infinite possibilities of the universe that surrounds us. As our exploration of protoplanetary disks and planetary formation deepens, it becomes essential to discuss the various observational techniques that have enabled astronomers to study these fascinating structures. One of the most revolutionary advancements in astronomy has been the development of high-resolution imaging techniques that allow scientists to capture detailed views of protoplanetary disks around young stars. Instruments such as the Atacama Large Millimeter/Submillimeter Array, ALMA, and the James Webb Space Telescope, JWST, have drastically changed our understanding of these disks and the processes occurring within them. ALMA, with its array of radio antennas situated in the high-altitude desert of Chile, is particularly adept at observing the cold dust and gas in protoplanetary disks. By detecting millimeter and submillimeter wavelengths of light, ALMA provides images that reveal the distribution of materials within these disks. For instance, ALMA has captured striking images of disks exhibiting gaps and rings, which are often indicative of planet formation. These features suggest that forming planets are gravitationally interacting with their surroundings, clearing their orbits and shaping the disk structure in ways that help scientists understand the dynamics of planetary formation. On the other hand, the James Webb Space Telescope, launched in late 2021, is set to enhance our exploration of protoplanetary disks further. With its infrared capabilities, JWST can observe young stars and their surrounding disks with unprecedented clarity. The ability to penetrate the dense gas and dust that shroud these disks allows astronomers to study the chemistry and temperature profiles within them. By analyzing the light emitted from different materials in the disk, scientists can determine the types of compounds present and how they change over time, shedding light on the conditions conducive to planet formation. Moreover, these observations not only provide snapshots of protoplanetary disks at various stages of their evolution, but also enables scientists to monitor changes over time. Long-term studies can reveal how disks evolve, how quickly planetesimals coalesce into protoplanets, and how the presence of multiple forming planets influences the dynamics of the surrounding material. This continuous observation of disk evolution helps paint a comprehensive picture of the life cycle of planetary systems, offering insights into their formation history and long-term stability. In addition to direct imaging techniques, spectroscopic methods play a crucial role in the study of protoplanetary disks. By analyzing the light spectra emitted by materials within the disks, scientists can identify specific molecules and understand their abundance. Spectroscopy can reveal the presence of important compounds such as water, carbon monoxide, and various organic molecules. These findings are critical because they provide clues about the building blocks available for planet formation and the potential for life in other systems. The diverse chemical makeup of protoplanetary disks is a subject of significant interest. The composition of these disks can vary widely based on the star's environment and its formative conditions. For example, disks around stars in dense star-forming regions may have higher abundances of certain molecules compared to those in more isolated regions. This variability has implications for the types of planets that can form and the potential for those planets to harbor life. As we consider the role of protoplanetary disks in the broader context of the universe, we must also acknowledge the intricate relationships between stars and the disks they host. The life cycle of a star and its disk is intertwined, with the star's radiation and stellar winds influencing the disk's evolution. As a star ages and transitions into different stages of its life cycle, its impact on the surrounding disk can be profound. For example, as a star moves toward the end of its life and begins to shed its outer layers, the materials released can enrich the disk with new elements, influencing the formation of subsequent generations of planets. Furthermore, interactions with neighboring stars can also play a significant role in shaping protoplanetary disks. In dense stellar environments, such as star clusters, gravitational interactions between stars can lead to the perturbation of disks, altering their structures and potentially triggering new cycles of planet formation. These interactions highlight the dynamic nature of star formation and the collaborative processes at play in the cosmos. The implications of understanding protoplanetary disks extend beyond our solar system. Each discovery of a protoplanetary disk around distant stars not only informs our knowledge of how planets form but also enhances our understanding of the conditions necessary for habitability. By studying the properties of disks across a range of stellar environments, scientists can develop models to predict the likelihood of Earth-like planets forming in different systems. As we turn our gaze toward the exoplanets discovered in recent years, the information gleaned from protoplanetary disks becomes even more critical. The growing catalog of exoplanets, many of which reside in their stars' habitable zones, demands a deeper understanding of the processes that lead to their formation. By correlating the characteristics of protoplanetary disks with the types of planets that emerge, researchers can refine their theories of planetary evolution and identify the conditions under which habitable worlds are most likely to form. Moreover, the study of protoplanetary disks opens new avenues for investigating the possibility of life beyond Earth. The presence of organic molecules in disks, along with the discovery of water ice, raises exciting questions about the potential for life-sustaining environments elsewhere in the universe. Understanding how these materials come together during planet formation can provide insights into the origins of life itself, and the processes that led to the development of habitable conditions on Earth. As we continue to explore the cosmos and unravel the mysteries of protoplanetary disks, we must also reflect on the profound implications of our findings. The pursuit of knowledge about the universe is not merely an academic endeavor, it is a journey that connects us to the fabric of existence. Each discovery enhances our understanding of where we fit within the vast tapestry of the cosmos, and inspires a sense of wonder and curiosity. The future of planetary science promises exciting developments, as ongoing missions and technological advancements are poised to reveal even more about the intricacies of protoplanetary disks and planet formation. With the potential for new discoveries on the horizon, we are reminded of the profound nature of our quest for knowledge and the importance of curiosity in driving scientific exploration. In this age of exploration, our understanding of protoplanetary disks represents just one piece of the puzzle in the quest to comprehend the universe's origins and the conditions necessary for life. As we venture further into the unknown, we carry with us the legacy of generations of scientists who have sought to unravel the mysteries of the cosmos. Each step we take brings us closer to answering fundamental questions about existence and the potential for life beyond our planet. In conclusion, the study of protoplanetary disks and the birth of planets is a rich and dynamic field that intertwines astronomy, chemistry, and planetary science. Through advancements in observational technology, we are uncovering the secrets hidden within these disks, gaining insights into the processes that give rise to diverse planetary systems. The continued exploration of protoplanetary disks promises to deepen our understanding of our own solar system and the countless worlds that populate the universe, reminding us of the infinite possibilities that lie beyond our small blue planet. As we ponder the nature of protoplanetary disks, we are invited to reflect on our place within the universe and the potential for life to thrive in diverse environments. The mysteries of planetary formation inspire a sense of wonder and highlight the interconnectedness of all things in the cosmos. With each discovery, we draw closer to understanding the origins of the planets that orbit our stars and the remarkable stories they tell about the universe we inhabit. As we conclude this exploration of protoplanetary disks, we are left with the realization that the pursuit of knowledge is an ongoing journey, one that invites us to look to the stars and contemplate the mysteries of existence. The story of planet formation is a testament to the beauty and complexity of the universe, and it serves as a reminder of the endless questions that drive our scientific inquiries. In the grand scheme of things, we are but a small part of a vast and wondrous cosmos, yet our quest for understanding connects us to the stars and the timeless mysteries that lie beyond. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.